So my name is Arno Kolster, and I'm principal co-founder of a company called Providentia Worldwide with my colleague Ryan Quick. We used to work at PayPal, so you might have seen us talk a lot more at the previous user forums. This is actually my 5th anniversary of the user forum, and Steve keeps inviting me back, so I must be doing something right. Either that or he needs a good comic relief now and then. But the first time I spoke at a user forum when I was at PayPal, we talked about fraud detection. And it was quite exciting for us to be here because we were more or less the first industry speakers. And we were talking about fraud detection. And I have to tell the story because most of you I recognize from being there 5 years ago. But what happened was I was listening the first day, and I'd hear all these great HPC stories about, we're running on 300,000 cores and we're running on 500,000 or 400,000 cores as Blue Waters. And I said to Steve at dinner that night, I said, Steve, you really want us to talk about our 192 core system? And he said, yeah, they'll love it. So we're still here. But what we're going to talk about now, I usually talk about big data and streaming analytics. What we're going to talk about now is what our perceptions are of where machine learning and deep learning is going in the next couple of years. But then I decided that it's probably better if we talk about the next 3 years because there's a lot of changes happening in the marketplace as well as the research that's being done. And it's very exciting, like Dr. Wang said, it's very exciting from an HPC perspective, but also from an industry perspective because both entities are coming together to solve these big problems. And you've got Google and Facebook and Baidu and a little bit of eBay. They're all working on these huge machine learning problems, and then you've got the research scientists that you just saw from NSF that are basically doing the same thing. So having the two entities, industry, commercial, private companies, plus the academia and research science communities coming together to solve some of these problems is quite amazing. So we saw the great video of the tornado this morning, and we saw a great video of Nissan's self-driving car yesterday. I don't have any of those things, but I've got a robot. And so I was actually going to have the robot do the talk, but it got its training at Facebook, and it was unintelligible. So I took this slide from NVIDIA, and Dr. Wang showed something similar. Many of you, well, maybe Paul and Vince, back in the 60s, probably saw this same kind of thing with artificial intelligence and machine learning and deep learning. But like the previous speaker said, in the last few years, it's really taken off due to 3 things: algorithm changes, GPUs, and big data that's necessary to drive the learning. So that's quickly an overview. And it's a good thing I don't have to teach any of that because you already heard in the previous slide. And you'll probably come away this afternoon with more deep learning and machine learning information than you really wanted to. But basically, let's see. What you see underneath here is the neural network that Dr. Wong's talking about. And you input an image. In this case, it's a cow, and out comes yes or no. It's a cow in the image. But like he demonstrated, it becomes very, very complicated and very, very complex. And what we're really trying to do is mimic the human brain. So we're always constantly learning. And in a previous talk about streaming analytics, I've talked about detecting anomalies in real time, especially when you're listening to music in a live setting. You can detect a note immediately if it's wrong with your brain. And that's because you've been trained, your brain's been trained since birth to listen to music that sounds good. But if you hear a bad note, you can recognize it immediately that it's something wrong. So the other night we were in the lounge, surprisingly, and there was a great lounge pianist playing. And even though we didn't know the songs, we could tell it was really good. He was a really good player because he didn't have any bad notes. And this is sort of the same thing we're trying to do with neural networks. You're training the neural network to understand inputs and outputs and have it determine whether it's good or bad. So that's a very simplistic view of how it works. But again, it's very, very complicated. And it can drive so many really cool things as demonstrated earlier. So let's talk about some machine learning projects. What's it like to actually try and do one of these now? So when we were at PayPal, they asked us, because we had a small supercomputing cluster from SGI that we're using for fraud detection, and they said, oh, those Arno and Ryan, they can go fix this, figure out this problem. And the problem is that at PayPal, for instance, there's literally tens of millions of files on file systems across the whole company. Any large company has tens of millions of files. Even my laptop, my Mac laptop, has about 800,000 files on it. The real problem was PayPal or any credit card company or anybody was looking for files that had credit card data in it. Very simple. They're looking for 16 numbers in a file somewhere because they need to scrub that out. PII is a very important security problem. Credit card numbers in a clear is very important. We need to get rid of those. So they said, okay, you guys have a small supercomputer cluster. How can you solve this problem? So we looked at it and basically we said, okay, whoops, go back. Here's an input. These are all the files on all the file systems everywhere in the company, right? And so we calculated it out. If you took each file and you opened it to see what type of file it was, is it a text file, is it binary, is it a Hadoop file, is it a MySQL CSV file, is it an Oracle data file? If you did that for tens of millions of files, it would take years, right? So we said, okay, let's apply some machine learning to it to understand what each of the files are. We can do it simply by looking at the file name, right, a text file or a CSV file, or potentially just open the file briefly, see what's inside, classify the data, and then carry on. And you could do this thousands of times a second across all the files. So now you're reducing tens of thousands of hours down to seconds using simple machine learning. So essentially what we're doing is taking metadata of the file, the name, the type of file, the size of the file, dates and times of creation, et cetera, and cluster those together. So we have this constant input stream of metadata that's being clustered together to say, okay, these are all CSV files, and these are all Oracle binary files, these are all executables. And so what that means is you're clustering by nearest neighbor, you get a histogram, and then you're classifying the files. So you've got histograms of X numbers of text files, X numbers of CSVs, Excel, et cetera. If we're interested in text files only, because credit card numbers in the clear are basically text, we can determine whether or not these particular files we're looking at has a potential problem, i.e., is there a credit card in there? So we're detecting patterns of interest here. And our good friends from Rift, who aren't here today, we're using a Rift 1 to basically grep through the files really, really quickly to determine whether that particular 16-digit pattern was in that file. Now, it doesn't have to be credit cards. It can be anything you like, i.e. addresses or names or anything text-related. So get the pattern match. If the file says, yeah, there's a text pattern that matches what we're looking for, send a notification out and flag that file as being suspect. So this is an actual workflow that we put together that's using machine learning at a simple level, i.e. clustering and pattern matching, to determine whether or not to flag files. And because it's done by computers, it's much, much faster than it could be done by a human. But the real problem here is you have the same diagram on the right side. You're using a whole bunch of different technologies to do that. So we're using messaging, because everything's streamed. Messaging is the glue that we're using between HPC and the enterprise. We're using a metadata schema, so we're updating a relational database. In this case, it was MySQL, to keep the metadata store of the files we've looked at, how many occurrences we found. Do we have to go review that file again in the future? Perhaps a developer left clear text again in the logs. We're using both supervised and unsupervised learning against those files so that we would take the output from the Rift box and say, okay, there is a credit card here. It looks like it's 16 numbers straight, or maybe there's 4 and then 4 with spaces. There's a lot of different varieties, but this is kind of supervised learning. And then we have The pattern and anomaly detection, i.e. we're looking for names or certain warnings. In our streaming analytics project, we were looking for things like error, log, warning, things that could be disastrous for the servers. And then we generate events out of that to be able to send information. But what I'm trying to illustrate here is, sure, there's a little part of machine learning and a little bit of deep learning there, but there's an ecosystem around this that's required for you to complete the workflow. And I think the fellow from NVIDIA this morning, I think it was Dale, that's the name, he said the same thing. You need an ecosystem and a workflow that has to be there for you to maximize the potential for the learning programs. All right, so we've got the same components on that side, but what I'm trying to show here is you've got dependencies between a bunch of different components. And in this case, the use case is very specific. We talked about the general use case, which I'll talk about in a second, but everything's very use case specific. We're looking for stop signs, we're looking for yield signs. We're not looking for cats on stop signs, but what I'm trying to show is that the pieces that are being used can only be used for one particular item. And in this case, the clustering engine, the classification engine, the pattern detection engine are all being sent to the message bus, and the data marshaling is necessary for you to continue. You've got the relationship for the metadata and updating the metadata scores, et cetera. Watching the time here. All right, so the state of things today, machine learning, deep learning have to be part of a workflow for them to be any meaningful. It's great that researchers are able to determine cats are on pictures, but unless you have a need for cats on pictures, it has to be part of a bigger workflow. It's also very difficult for commercial, there's a lot of commercial and open source software out there, TensorFlow, AML, Apache Mahout, Apache Spark, et cetera, they're making great strides in algorithms and driving that research. Interoperability, we heard that earlier today, workflow management, there's a lag between how the applications work and how you get it to the rest of the system. We feel messaging and eventing are required. A lot of these things, like Apache Spark, is basically streaming data in and working on it. And the lines between supervised and unsupervised deep learning are very blurry. There's a lot of research still going on, and that's not solidified yet. Overfitting is a real problem. Overfitting is basically the complexity of a deep neural network, and potentially the deep neural network isn't learning as much as it used to. It's being basically memorizing what you've taught it, and that's a real problem in a different number of areas. All right, so development style is also different. We're dealing with companies who have a lot of research. There's a lot of developers that are developing on laptops, for instance, because every Mac has a GPU. So there's a lot of independent kind of research being done outside of the norm, and that makes it a bit interesting. Algorithm and data formats are very closely linked together currently. So if you're looking for text data, you're going to look at text files. If you're looking for image data, you're going to look at image files. The general case is not there yet, where you can say, I want to find the word cat in tags in a image file. So it's very experimental. That means operational requirements are not there like it should be in a productionized system. And performance is tied to technology choices per use case. So either you're using GPUs or you're using FPGAs or you're using CPUs for data marshaling, et cetera, et cetera. All right, so let's talk a little bit about machine learning systems and where things are, what we think is going to happen in the next few years. So the perfect system, the ideal system, kind of takes everything that we've learned so far and puts it together. So basically, workflow management, the whole flow that I described before, is going to be part of the design up front. There's no way you could build a deep learning system and then not have the ecosystem around it to support it, either ingestion of data or analytics of data, or the visualization of the data. Event management and message flow are the glue and the integration points between all the systems, including HPC to HPC, HPC to enterprise, enterprise to HPC, et cetera. So using open source or proprietary information, messaging streams, you can basically send data back and forth and basically glue the components together. The choice of data set and algorithms is dependent on what you're going to be using it for. And so in a general case, the perfect situation, you should be able to input data and with a parameter and then get the right result back depending on what you're looking for. Similar to the human brain. I could listen to music and tell you bad notes. I can read a book and spit out the information back in Spanish, let's say. But the inputs are all going to the same place, which in our case is the brain. Acceleration is going to be very dynamic. We're going to, in the near future, we'll see different types of accelerators drive further research as well as further performance. And this is all happening dramatically. The shift of technology in the last few years has increased dramatically. Analyst tools are easily understood, run on all platforms, and support SME language. Very important, because the people who are basically teaching your deep learning network have to be subject matter experts. And the tools they use, in this case it could be natural language to drive the actual training of the network, is very important, because subject matter experts are not developers, and developers are not subject matter experts. And without the two of them, you can't really build what you're looking for. So that's very cool. Visualization capabilities are coming. Either it's going to be browser-based or virtual reality or something along the lines to make dealing with the neural network a lot simpler and a lot easier. And then, of course, you've got all the operational aspects of the system. All the NOC tools need to be there. All the key value performance indicators need to be there. And that's basically just a normal production operation sort of thing. All right, so for the next year to year and a half, we see we call it the era of use-specific systems. Systems that only do one thing. You put in, is this a picture of a cat? Yes, it's a picture of a cat. Is this a picture of a dog? Yes, it's a picture of a dog. So these are very use-specific. We want to get to the general specific case, which is going to be a few more years out from what we understand. But we do want to collate use cases. So for instance, self-driving cars, is this a stop sign? Yes. Is this a yield sign? Yes. Is this a detour sign? Yes. Those three things can all be done with the same deep learning methodology. So you're sort of collating the use cases instead of having three networks. You could just build one with many different layers. We rely on ontologies, i.e. the events that are happening among different spheres of influence, as I like to call them. You could put those together and understand the ontology and the data structures around that. We want to teach the SMEs, like I mentioned earlier, about how to talk to the developers to let them understand that this is how the business or function I'm looking for will actually work. And the developers have to understand the SMEs to the point where they have to say, okay, this is what the business rules are, how do I code that? And each of the two parties are happy. Like I mentioned earlier, there's a lot of folks developing on laptops, which is great because it's cheap, it's easy to use, you don't need a huge cluster to do that. But once you get that to a state where it's running pretty good, you could go to a smaller cluster. And a lot of people are going to say, well, scale up instead of scale out. We come from a hyperscale world, so we like to scale out first and then scale up. The fact that we're sort of suggesting maybe 8 cores or 8 GPUs per node and then scale out a little further is probably a better way to go because you don't really know what's happening next, and it's a lot cheaper way to move that way. All right, workflow management again, very important. You need to understand the whole workflow. probably going to get a lot of flack over this next one. Codes are antiquated and inefficient. Potentially, yes, but we're building huge HPC clusters to keep the codes around that we've had for 25 years. There's new technologies out there, new languages that might make those more efficient. Each learning system is very distinct. This is another point of misinformation. If you have a neural network in San Diego, for instance, you can't replicate that same neural network to Washington, D.C. They're completely different. In terms of enterprise, yes, you can have a database backup or a database replication in both locations, and the data will be the same, but a neural network is completely different. So if anyone's trying to sell you one that's replicating, it doesn't work that way. The reuse of the system is limited because of the issues we talked about above. Expect to build several neural networks to do various different things in the next couple of years. All right. So we're going to gain some economies of scale, and we're going to build more tools for analytics. These are all coming. Algorithms will continue to improve, but are still specific to the data set. So image recognition or speech recognition are going to still be specific to the data set and to the accelerator, either GPU or FPGA. A year and a half to 3 years out, we're going to continue the scale out. But what's happening here is, as Mellanox mentioned this morning, you're going to see a few different things happening in hardware that we weren't expecting before. So there's going to be more network compute. There's going to be more analytics on the wire. And there's going to be more. This will allow for more algorithms to be generalized, because now you can actually start to develop data on the wire before it gets to your neural network. And the standards for the popular algorithms will allow clusters to be collapsed. So for instance, the 3 or 4 clusters we had for recognizing images, they can be collapsed into one, because GPUs and workflow management will be much better. So like I mentioned, a year and a half to 3 years from now is going to be the generally specialized system instead of the specific use case. So everything's continuing. The visualization is going to be there with potentially, like I mentioned, virtual reality. And finally, the systems will be integrated with your operations rooms. They'll be productionized just like all the applications are today, and will be much better off because commercial entities as well as open source will be merging together. The HPC researchers and the industry will also be running together. Steve just gave me 2 minutes. 2 minutes up. So that's my name, and and I've got another robot there. So any questions?
Steve. Yeah, I got a question, which is, you were talking about message passing being the glue between HPC and the enterprise, but sort of getting this technology into it. What about the business units as opposed to IT as this as the starting point? Where is this going to start? Is this going to be lit, is the match going to be lit in IT, or is it, as I think in some ways happened in PayPal, maybe a business problem comes up?
It's a business problem, for instance. Well, I'll take eBay because I don't work for PayPal anymore, but eBay and Baidu are working on image recognition of, if I want to buy a hat like Rich has on his head, I just take a picture of it and I go to eBay and I say, give me all the listings on eBay that match this particular item. It doesn't know what that item is, it just knows it's a red hat. But somehow it managed to figure out, here's the listings for all the red hats, and I can buy one immediately. So that's a business requirement to actually have a mobile phone to say, I like that person, that woman, can I just take a picture of it and then go buy it right away? Not even knowing how much it costs or where it came from.
So if I'm selling to, like, I've said this before, if I'm selling to a major hospital system or something like that as a vendor, am I better off going in talking about IOPS and stuff like that, or am I better off talking about how many cancers I can detect per second?
I think it's the end case, saying the really cool stuff. I can detect these cancers I can drive sales up for Red Hats. They don't want to understand the underlying technology. They just think it's cool that you can do these types of things. And they have the money. The IT people don't have the money.
Scale-up model?
Yeah, scale out, scale up.
So that's a 36 months if you've been into AI, tested out, done the scale-out version. What is the scenario that you define as scaling up kicks in?
You'll end up scaling up and out. Sorry, you'll end up scaling out and then up. That's a typical model from the hyperscale world because you're locked into, if you go scale up right away, you're locked into that model. Going scale out, it sort of gives you a parallel path right away, and then when you move higher, you're basically able to grow scale this way. So you could go wide and then up. It's like a diagonal instead of. Go ahead.
So maybe this question is related to that one in some odd way, but suppose I'm in a business ecosystem in which I have a lot of different parts of my organization that have different but related business challenges that might be amenable to different types of deep learning, machine learning sorts of approaches. But the different parts of the organization have, it may be they're working with different vendors, they're using different systems. Can you envision an ecosystem, or is there work being done in how to put together an architecture, an ecosystem that would enable a diversity of machine learning approaches, deep learning approaches to sort of function together within that ecosystem while being able to synergistically work together? In other words, they're not just sort of all silos that have to do their whole vertical stack on their own separate from others, but can share data and share things where it makes sense to do so?
Yeah, you can definitely do that with messaging. You're basically sourcing the same data from one place maybe, and then you can pass it through all those systems for them to do this different things on the same data.
To what extent does that require sort of sharing inside the black box of different approaches? We, in our organizational context, we run into issues in which sort of how the architecture of the neural network or the particular algorithm, that's the secret sauce of that organization, and they don't want to share too many of the details, or maybe any of the details, because they feel that it puts their business value at risk.
Yeah.
And so there are some, there are limits into what individual vendors may be willing to share with each other.
No, it can be done. If you're comfortable with sharing the data between, if you have one source of data, let's say the Red Hats, for instance, you've got the marketing folks that want to market that Red Hat. You've got the business unit on the back end saying how many Red Hats have we sold. So you're sharing that one piece of data amongst different business groups, and you can definitely have different deep learning algorithms running against the same piece of data. Does that answer?
It does. I guess I was also a little surprised to a lesser extent by your comment that you sort of can't necessarily share neural net learning between systems, right? If I train and learn to do a particular type of classification activity over here, I can't necessarily take that learning and move it over here and reuse it.
I think you can't replicate it in terms of traditional enterprise where you have a database here that's being replicated to this other one, because this neural network will behave different than this one, even if it's the same parameters. It has to sort of learn itself again. It's like if you have twins, if you have twins and you're teaching them the same thing, they're going to be different. It's a weird example of
I
that.
understand what you're saying.
So rather along that line, you were talking about, or you mentioned your ontological challenges. So you pick it up, you learn an ontology, but then you have a hard time promulgating it. Are you creating an ontology for each instance, or are you actually able to negotiate ontologies across organizations or across instances?
Both.
And do you have a mechanism to do that as the center of gravity for it, or is there some governance that you're using to do that?
It's basically trying to determine what ontology/data set or metadata set would work across the organizations. Does that make sense?
Well, so are you finding that under the nearest rock, or is that?
No, you have to custom build it.
Okay,
Yeah.
Roger. Thank you.
Thanks.
Arno, thank you very much.
Oh, you're welcome. Thanks.